Let's go back to another distance vector algorithm, BGP, the Border Gateway Protocol. This is used between autonomous systems. It is a distance vector algorithm. So basically it does use hop count, but it's not in between individual routers, it's in between autonomous systems. So let's say we have these three autonomous systems. Now, let's say they're also connected and have a direct connection, as we've shown here. Now again, inside of each one of these autonomous systems, you're typically going to have open shortest path first, or ISIS, intermediate system to intermediate system. So what happens here is that from each source autonomous system to each destination autonomous system, the routes are determined. If we have this type of topology between autonomous systems, there are multiple paths that are determined by the Border Gateway Protocol. Let's take a look at how we would reach each different autonomous system. So let's say we wanted to go to level 3, and we were from Nippon Telephone and Telegraph. Well, to get to level 3 from Nippon Telephone and Telegraph, we could either do AS1 or we could do AS3 to AS1 because we've got redundant paths. Let's say I wanted to go get to AT&T from level 3. So to get to AT&T from level 3, I could either go directly to AS3 or I could go through Nippon Telephone and Telegraph and then go to AT&T. Or let's say I wanted to reach Nippon Telephone and Telegraph from AT&T. So to get to Nippon Telephone and Telegraph, I could just go directly to Autonomous System 2, or I could go to Autonomous System 1 and then go to Autonomous System 2. So these are the types of routes that you would see in a Border Gateway Protocol routing table. Now these are not going to change very frequently because new autonomous systems are not added as frequently to the internet. So the complete paths for each autonomous system to each other autonomous system are actually known. Now there are millions of paths stored in these RBRs, these really big routers that implement the Border Gateway Protocol. These autonomous systems are maintained by the large telecommunication or internet service providers. Now, it's not strictly a distance vector algorithm because there are also peering agreements that are made between these different AISPs and telecommunication providers, which specify what the paths are going to be between each one of these autonomous systems. Now let's next look at a hybrid algorithm. the Interior Gateway Routing Protocol actually uses a number of different metrics to find the best path. Now, because IGRP was rather restricted, and it also had routing loops, there's actually an improved version, which is the enhanced IGRP. And it also, in addition to eliminating the routing loops, is it also supports variable length subnet masks. Now, another huge advantage is that the data packets can actually be sent across parallel paths. Now, similar to OpenShore's Path First, it actually determines the topology based upon advertisements from its neighbors. Now, IGRP and Enhanced IGRP, these are proprietary algorithms that are owned by Cisco. You would see them used within an autonomous system. Now, let's take a look at the metric that's used to determine the best path for IGRP. So our metric is going to be a number, K1, that we would input times the bandwidth that's the throughput. So it does partly use a link state algorithm. Another constant, K2, that will multiply by the bandwidth. But it also works with the load. Remember, the load was a metric of how much information is being sent through that particular router. We've got another value, K3. Again, this would be determined by the network engineer, times the delay. And delay could be caused by multiple things. It could be the router was slow, it could be due to congestion on the router. We've got another constant we would define, K4, which is going to be plus reliability times K5. Now, the reliability needs is that how frequently is that network path up and available? This completes our chapter on routing. at the metrics that are used in dynamic routing. Now, one metric that you saw back in static routing as well is the hop count. That's the number of routers through which a packet passes to go from a source network to a destination network. And remember, each router that a packet passes through is going to be a hop. You've got throughput. This is going to be the speed of the connection between the routers. There's utilization. Even though there may be a lot of throughput, for instance, let's say you were using a synchronous optical network that had 155 megabits per second, but the utilization was very high. Let's say it's 99%, for instance, and you had a slower path, let's say a frame relay, that was only, let's say, at 2.048 megabits per second. The algorithm that implemented this particular metric would send the data over the slower path because there was more throughput available on that path. Depending upon what the maximum size of the packet, which can be routed by the router, you may not want to send the data packets on a particular path, because the larger the MTU is, the less overhead there is because of the header information. Now again, when you're figuring out what the router's figuring out what the best path is, hop count, you want a fewer number of hops, a fewer number of routers that you pass through. Throughput, you want to go through the fastest path. You want to go over the path that's least utilized, and you probably want to go over a router that supports larger MTU sizes. Now, a lot of times, utilization is referred to as congestion. Let's look at some other metrics. Cost. send data on a particular path. You'll see delay. Is the router slow? This could be due to congestion. And finally, we've got latency, the time to establish a connection. So again, you'd want to send the data packets over a less expensive route. You'd want to send those data packets through a router that is not slow. You want to send it through a faster router, one that's perhaps experiencing less congestion. And you might also send, again, your data across a path that has less latency. And again, this is the time to establish a connection that is required by the router. This ends our discussion of metro. You notice that in your classroom, the IP addresses were either on the 192.168.210.0/24 network or the 192.168.211.0/24 network. These are private IP addresses. They're not routable on the internet. In order for them to be routable on the internet, they have to go through a NAT. That maps private IP addresses to one or more public IP addresses. Now the NAT actually creates a table of mappings that show, for instance, an IP address that's on the private network mapped over to the public network. So, for instance, 192.168.211.200, that will be our source IP address, and we'll have an ephemeral port because we've got a client that's requesting a service of 54,123. What the NAT does is that maps that source IP address and source port to a different port. It maps it over to a port that's associated with 216.114.95.64. So in its table, it's going to have 192.168.211.200, port 54,123. It's going to be mapped over to 216.114.95.64. And it'll select another port number where it's being mapped. So when the data packet leaves this network, it's going to have this source IP address and this source port number. Now the destination stays the same. If you're connecting up to, let's say, a web server, and you're connecting up to port 443, which is for HTTPS, this is going to be the destination IP address and destination port number. When a response comes back in, that response to the request that's been sent out is going to be sent to 216.114.95.64 to this port number. Now when NAT sees that coming back in, it's going to say to itself, I need to send that data packet to this particular IP address and this port. Now why do you use NAT? Well, you save IP addresses. You don't have to have a publicly visible IP address for every single one of your clients. Secondly, it's for security purposes, because external attackers won't be able to access this particular IP address directly. And if they decide to attack a system, they're going to attack this system, the NAT, rather than attack your client's system. Now, there is a variation of this that's called port address translation, or PAT. This just maps over to one single IP address. NAT could actually map over to multiple IP addresses on the public network. Now, Cisco calls this IP masquerading. Now, another feature that you may see on the router is port forwarding. What does that mean? Well, let's say that we had a web server that was on 192.168.211.201 host. And let's say that web server was just using HTTP, so it's running on port 80. Now, if someone wants to access this web server, if they connect up to the NAT with IP address 216.114.94.68, that is the destination IP address. And destination port is going to be port 80. What port forwarding is going to do is it's going to say, hey, I'm going to send that packet that's destined for port 80 on the IP address 216.114.95.64 to this web server that's on 192.168.211.201. Now, you could even change this port if you wanted to run on a non-standard port, like port 8088 instead. Same thing will happen as far as port forwarding. If someone connects up to that port, port 80, and that IP address, they would get mapped over to this IP address and this port number. Now again, this is also for security purposes because if an attacker is trying to attack this system, it thinks that there's a web server running on this, an HTTP server, Hypertext Transfer Protocol server, rather than attacking this server that actually has that web server on it. This ends our discussion of network address translation, port address translation, and port forwarding.